Goal of this video is to try to shed some light on why this formula right here for the binomial distribution works. What are the components of this that cause it to give us the accurate answers that it does? Now, in order to use this formula, you have to be in the binomial setting. The binomial setting requires 4 conditions to be satisfied. You have to be in a spot where your trials involve a binary outcome. You win or you lose. You flip a coin, it's either heads or it's tails. You guess on a multiple choice question, you're either right or you're wrong. So there has to be a binary outcome. You have to have independence maintained from trial to trial, so the new trials are unaffected by the previous trials. That would be the case with coin flips if you're guessing on multiple choice questions. As long as the questions don't depend on one another, you're going to maintain independence in that case too. The number of trials is fixed. So that would mean we have a multiple choice test. There's 10 questions. We have to guess on all 10. We're flipping a coin 10 times. We're shooting a foul shot 15 times. The number of trials has to be fixed. And you have to maintain the same probability of success from trial to trial. So let's go ahead and talk about this particular situation. So we're going to flip a fair coin 5 times. We're going to define X to be the number of times that the outcome is heads. And what I've done within this table here took a little bit of time to do, but I think you're going to understand where this all comes from. These are the possible values that X can take on. I can either get none of the tosses to end up in heads, 1 of them, 2 of them, 3, 4, or 5 of them to end up as heads after they're tossed. What I did in this next row right here is I listed the sample space that represents that number of heads. So 0 heads would mean every flip is tails. So tails, 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 tails would be the only way that I could have 0 of the outcomes being heads. How many ways can I have 1 of the outcomes being heads? So what I did is I started as 4 tails in a row, the heads at the end, and then I just kind of moved the heads to an earlier flip. So here's the 4th flip, here's the 3rd flip, here it's the 2nd flip, and here it's the 1st flip. These are the 5 different ways exactly 1 of the outcomes can be heads. A little bit trickier for 2. So I said, okay, let's say both of my flips at the end up being heads. I kept that last heads in place, and I just moved the first instance of heads to an earlier flip, kept the last instance of heads in place as the last flip, moved that first instance of heads to an earlier flip, did that one more time here. These would be the outcomes that involve 2 heads that have my final flip landing in heads. What I then did is I moved my second instance of heads to the second to last flip, the 4th flip of the coin. So here's an outcome that has 2 heads using the same strategy. I've moved that first instance of heads to an earlier flip, moved it to an earlier flip. Now I'm going to move the last instance of heads to the 3rd position. So I could have 2 heads in this line or this line. And now I'm moving my last instance of heads to the 2nd position, and this would be the only way that I could get 2 heads with my last instance of heads being the 2nd flip. If you count up how many are here, you're going to get 10 total. Now, the nice thing about this is if you really take your time to identify what the outcomes are here, when you switch it to now 3 heads, all I did is I basically just switched all of these tails to heads, and all of the heads in the x equals 2 column to tails. So I have 10 outcomes there as well. When I went to 4 heads, all I did is I took a look at this column here where I had 1 heads, and I switched all of those h's to t's, and all of the t's to h's, and then the only way I can get 5 heads is if all 5 flips are heads, no tails. So how many ways can each of these outcomes arise? That's listed across this row. What is the probability of these number of heads occurring? Well, 1 out of, if you add up all of these number of ways across this row right here, you're going to get 32. So 1 out of 32 times, if I went through this experiment of flipping the coin 5 times, I would expect to get none of the outcomes to be heads. 5 out of the 32 times, I would expect to get 4 of the flips to end up heads. And the other corresponding probabilities are listed in that bottom row. It took me quite a bit of time to put this together. Hopefully it makes a lot of sense where this comes from. Hopefully it makes a lot of sense what we can do with this. Now, if we're asked a question like this, determine the probability exactly 2 of the flips land as heads, we've already put in all of the work. We've got 2 heads down this column, 10 out of the 32 different ways that this can arise give us 2 heads. So 10 out of 32, which reduces to 5 out of 16, which as a decimal would be 0.3125. So approximately 31% of the time, we're going to end up having 2 of our 5 flips end up being heads. Should make sense. Time consuming to arrange everything within this table the way I did, but hopefully this makes a lot of sense. The purpose of this formula that we saw on that opening screen, the purpose of this binomial distribution formula is to avoid having to go through the process of establishing everything that we saw within that table. So let's try to talk about the components of this formula here. So this is going to determine the probability that the number of heads equals lowercase x, right? The probability that our random variable equals a certain value of that random variable. Now n, which you'll see in a couple of spots in the formula, is the number of trials. In our case, that's been 5. X is the number of successful trials. So that's appearing here, here, and here. P is the probability of a successful trial. So that appears in 2 spots as well. Now, the one thing within this formula that's a little bit tricky and probably less familiar than a lot of the other components of it to a lot of you is what you see in this spot here. This notation that you see is going to determine how many different ways we can combine X successes among N trials. This formula, or this notation, requires use of the combinations formula. Here is how that combinations formula would look. So if you're not familiar with a factorial, what a factorial is, if I was seeing a 3 factorial within this numerator, for example, that would just be 3 times 2 times 1. Right? So we start with the value that's represented before the factorial symbol, and we multiply by every natural number down through 1. So we'll head to a new screen, try to explain the formula a little bit further. So here we are revisiting the question we already know the answer to. Determine the probability that exactly 2 of the flips, when we're flipping the coin 5 times, lands as heads. So we had this answer within that table that we took the time to construct. The purpose of this formula is to not have to go through all of the extra legwork, time, opportunities to make small mistakes, to build everything that you saw we had in that table a few screens ago. So I'm looking for the probability that the number of flips equals 2. So what's the probability that x is equal to 2? So what I'm going to be doing is I'm going to be putting 2 in place of the x's in the formula. So 2 is going to go in the bottom of my combination formula. 2 is going to go as the exponent on the probability of success. 2 is going to go as part of the exponent right after the subtraction on this calculation here. We'll talk more about that calculation soon. The number of trials is n, and that for our problem has been 5 throughout this discussion here. So I've put 5 in place of this n in the top of the combination formula, and I've also put 5 as the leading component of that exponent. And then the other thing, when we're flipping a fair coin, half chance it ends as heads, half chance it ends as tails. So I've put 0.5 in place of the first instance of P, and I've also put 0.5 in place of the second instance of P. Okay. Before we do any more work with the combination formula, let's talk about these 2 components here. I'm measuring the likelihood that 2 of my flips are successful. The probability of success for independent events for 2 successes would be 0.5 times 0.5. What you see here is you see 0.5 squared. So the probability of flipping the coin twice and having it land heads both times is 0.5 times 0.5. That's what you see right here. Now I'm multiplying this by the extra component that you see right here. Now think about how this exponent simplifies. If I'm measuring for 2 successes, that means I'm going to have the number of trials minus 2 successes as the number of failures. 5 minus 2 is obviously 3. This is a complement right here. This would be the probability of failure. Now for flipping a coin, the probability of landing heads and the probability of landing tails would be the same. Now if this was like guessing on a multiple choice question and the probability of guessing correct was 0.25 because there were 4 options for you to choose from, this would be a 0.25, and then 1 minus 0.25, this would be a 0.75. This base right here is the probability of failure. In our case, the probability of heads and the probability of tails is the same, so for this particular problem, they both end up being 0.5, but this is the probability of failure in this set of parentheses. That obviously simplifies to 0.5, and we're measuring for 3 of the 5 total flips to be failures. So the probability of getting 3 failures in a row would be 0.5 times 0.5, times 5 for independent events, which is why you see a 0.5 to the third in that position. So what is going on with this combination formula? I'm going to go to a new screen, right? I've got the 5 and the 2 plugged into this, so we looked at this formula a little bit on the last screen. I'm going to go to a new screen to talk about how this simplifies. So if I write out 5 factorial, and I write out 2 factorial, and then I think about 5 minus 2 being 3, and I write out 3 factorial here, check out what that allows me to do. I can do quite a bit of cancellation here. 3 times 2 times 1 within the numerator can cancel with the 3 times 2 times 1 in the denominator. What's my numerator? 5 times 4. My denominator is 2 times 1. 20 divided by 2 is 10. That should look familiar. What this calculation right here does is it allows us to figure out that there are 10 ways to have 2 of our 5 outcomes be heads. It determines all of the different combinations of ways that we can have 2 of the 5 outcomes be heads. We don't have to list them all out. Now, whenever you only have 5 trials, it doesn't take that long to list these out, but what if you had 10 trials? You're not going to want to list out all of the possibilities that result in 2 heads when you have 10 trials. It's going to be way more than any of the numbers that we see within this table here. So the whole purpose of this calculation is to allow us to figure out how many ways we can have. The whole purpose of the combination calculation, I should say, is to allow us to figure out how many ways we can have 2 of our 5 flips end up as successes, 10 in our case, and what I'm multiplying the 10 by is the probability of 2 successes and 3 failures. And in this case, that ends up being the same answer that we got from the table.